Okay, now we're done with the localization of the sample. So next step, we're going to set up the laser and the area scan system for a super resolution use. So here we go to the acquisition tab, just click here and you'll notice that, um, wait a second, okay, here we are. So we're done with the now we are done with the localization of the sample we are trying to look at. Next step, what we're going to do is we use this acquisition mode to set up the parameters for area scan, for super resolution, and for all the dyes that we are using. So, for example, here we use our calibration chip, and I know that they are standing with two different dyes. So what we're gonna do is, let me just restart a new one. So calibration use. This is set up a new remembered parameters for future use. So we just click save. We have nothing here. Okay. So now for in the future, if you already set up the parameters, for example, we have like some document for the picogram use, some for the Stanford project CDM use, and some for the photo bleaching test. These are all preset by me, but in the future, you can, whoever used the area scan, you can set up the document for yourself, so you don't need to set it up every time you're doing the experiment. Okay, so now we know that we have two different kind of dyes on our sample. So we first hit this smart setup. We are using here you can choose to use the confocal or area scan. So we want super resolution, so we touch the area scan here. And we want high resolution, so we choose here at the edge of the resolution. This is the area scan SR, just one click, and then we add the dye we want to look. So here in area scan, we already have the database for a lot of different kinds of dyes. Those most commonly used in our lab is like the Mito tracker. Yeah, we have the common Mito tracker green here, and Mito tracker deep red and Mito tracker orange. And on the top here is the recently used one. So we will, for this test, we're going to use one green and one orange dye. So I'll use Mito tracker green as the green one. Just double click, they will add in directly. And then I'll use the TMR, which is stand for the TMRE, and double click in, and then we close here. And you can notice that you have different choice for the settings. One is the best signal, the other is smartest. So you will notice that the different part of these two settings are the overlapping of the two laser emissions. So smartest setup is for if you is automatically set up for higher speed and also higher like performance on the image, but with a little sacrifice on the overlapping. But if we are doing some kind of experiment like the Stanford one, we need to like we definitely need to like separate the wavelength, emission wavelength for different dyes. Then we'll need to use the best signal setup. Here it will cut off the different range for the emissions. So once you choose it, hit OK. And here the system is setting up for you. So on the channels here, we can look at, we have two tracks here, image setup and channels. This controls the emission and intensity of the laser and also the excitation. So for track one, for example, TMRE, here we can see that the the laser we use for this dye is excitation wavelength is 561 nanometer. The intensity is currently set to 0.4%. So for normal use, 1 to 2% of the intensity is good enough for most of the cell images. And we recommend not to use over 5%, but if you turn this one, the high intensity laser range up, you can use larger range of the intensity for a certain condition that you need. But because this laser, it will cause phototoxicity and photobleaching to the sample, so we don't recommend you to use too high laser intensity. Usually we'll set to like 1 to 2%. And here on the bottom, you can see the master gain here. This is the setting to like better separate the intensity you are looking at and also the background. So here, the background. And so for this scan, usually we set from 700 to 900. And this is commonly used, but it depends on your the quality of the image you have right now. So, you can adjust it by yourself. And if we hit the track 2, here's the green dye that we use the 488 for excitation. The same thing here is you can change the intensity of the laser, the digital gain. And you can also, here at the image setup, you can also change the emission range if you are, like, for example, if we're using 488 excitation, anything below 488 should have very low intensity, and you may not want to like include them. In this case, you can just click here and adjust your emission range. For example, here is 450 to 550. You can set to 488. And then it will change the green dye emission from 450 to 550 and change it to 488 to 550. So these numbers are not fixed. You can always change the emission range by yourself. Okay. And that is for the dye part. And here on the top acquisition mode tab, section panel here. So this is the panel for you to like adjust the size of the image. And right now, the widest we're having right now for the image is 245 micrometer times 245. And the pixel size is 0.07 micrometer. And if we, let's just take an image first. So let's do live imaging. And now what we can see here, in the green fluorescence dye, we see very low intensity because the green dye is, I think this sample is very dim. But if we look at using the orange dye to look at it, you'll notice that there's a very beautiful image of the orange dye. And this right now here, the frame time is telling you how much time it needs to take. It needs for one image taken. So you can always you can adjust the scan speed over here. It will tell you how much time one pixel is gonna need, and all the pixel, how many pixels you have here right now is 3,300 times, around 3,300 times 3,300 pixels. So you can always tap it maximum to increase the time, to lower down the time for each frame to take. For example, this image, for this size of the image with 2 channels of the laser, it takes 30 seconds to take an image. And if we don't, and if we only want one channel, we click it off, you'll notice that the frame time decreased. So right now, let's do one image with these two channels. Let's just take the snapshot and wait 30 seconds. You'll notice that it will like scan the orange dye first and the green one. You can always set the maximum and minimum to see the overlapping of the images. Or if you only want to look at one, you just click here the tab to like hide one of the fluorescence. Okay, so now one of the images down. This is the image we are taking, and you can go to the info here. It will tells you the name of this image, when does it create, and go down here. The size of the image, how many pixels, size of the image in the micrometer square unit, and the channel informations like the pixel time, the frame time, the intensity, or everything here. Okay. And here this the crop area. If you click it, it will like for you to see like a smaller range. For example, if we only want to look at a certain area, we can make it down and then focus to the place we want to see, for example, here. And it will tell you it's like a 5.9 times bigger. So, and you'll notice that for this small range of image, it only takes 1.79 seconds for them to take one frame of the image. So, and this one is pretty good when you are trying to see only a certain, very small certain area within the cells. For example, one single mitochondria or the nucleus. And because the frame time is so small, it will reduce the photo bleaching effect to the certain place. So we can just take a snap here, and we'll notice that it is going to take an image of the area that you're looking at. Okay, but here, go to the info. You'll also notice that the image pixels are less, but the scaling is the same, because the scale or we call the resolution of the image depends on the lens you are using. So under the lens we're using right now is 20x, the pixel size is going to be fixed, no matter if you're looking at the small or the bigger one. But then you will say, oh, well, if that's the case, then we'll just do like the whole view image and then just crop the part we are looking at. But the problem is in cells, usually, for example, mitochondria inside the cell, all these organelle is gonna move when you are taking the image. So the longer time you take the image, the more possible they will move and gonna blur the image out. So it is important to see to define what's the question you are looking at. If you're looking at something that is mobile and move fast, then it will be recommended to use the crop area to look at the specific area you're looking at. Okay, so this is basically how to do the images using the acquisition mode.